Okay, guys, today we can start Unit 2, which, which is all about sequential logical circuits. We are already studied about the combination and sequential logic circuit and their difference. All of you know about what is combinational circuit is and what is sequential circuit is. Okay, combinational circuit is nothing but there is no feedbacking. Okay, there is no feedbacking as well as there is no memory in combinational circuit. In case of sequential circuit, there is feedbacking, and uh, the feedbacking results the, the need of memory. So there will be a memory in a sequential logic circuit. Normally, electronic circuit will be the combination of sequential and combinational circuit. Okay, first of all, we are going to take a look on triggering. So, first you have to understand what is triggering is. Triggering is nothing but it is a momentary change in the control input of a flip-flop to switch a flip-flop from one state to another, which is called a trigger. The process of applying this trigger to the input of the flip-flop is known as triggering. Triggering will cause a change of state of a flip-flop from one to another. Okay, there are different type of triggering. First one is pulse triggering and edge triggering. Pulse triggering comprises of high level triggering and low level triggering. You can see in the image, high level means the higher level of the clock, which is used for the triggering purpose or changing the state of a flip-flop from one to another. So if you are giving the clock as high level, then the state of the flip-flop will be changed. Then it is high level triggering. If you are just like the opposite, low level triggering, which means that lowest level, the just the opposite level of the clock pulse will result to a change in the state of a flip-flop, then you can say it is low level triggering. Okay, then this is all about pulse triggering. Moving on to edge triggering, there is two type of triggering. They are positive and negative edge triggering. Positive edge means the edge is starting from the falling level to the highest level. Then you can say the positive edge. In that image it is dark, shaded. So the positive edge is from the low to high transition state of a clock pulse, which is shaded in the figure. If you are giving this portion as input, as a clock, for a flip-flop, then its state is changed. You can say it is positive edge triggering. Which combines the falling edge, that is from high to low edge of a clock pulse is giving as input, as a clock input to the flip-flop, then the state is being changed, then you can say it is negative edge triggering. Okay, this is all about triggering. Then you have to understand what is SR latch is. Latch is nothing but hold in place, that is a memory device. The basic memory device is known as latch. Okay. In computer, we all know we are giving some data and it is being stored and then being processed, and the result is again being stored somewhere else in the memory. And when you need the data, you can access it from the memory. So the practical or the actual implementation of this memory in the form of latches and flip-flops. Okay. So, latch is a memory device. Here you can study about XR latch, and the circuit symbol is as depicted in the figure. Okay. Moving on to the truth table, you can see S and R as inputs and Q and Q bar as output. If you are giving the value S and R as 0, S and R is the short form of set and reset. Setting means you are setting the circuit, sorry, the setting the state of the flip-flop to 1. Okay, setting the state of flip-flop to 1. If you are giving set S value as 1, you are setting the value of this the present state of the flip-flop as 1. If you are giving R as 1, then you are doing the reset operation. Okay, let's see what's happened when you are giving 0 0 as S and R. Then Q and Q bar will be the output you are getting from the SR latch. If you are giving S and R as 0, then there is no set and no reset operation. So the previous state is continued as it is. Okay, then if you are giving 0 and 1 as a combination, that is S is 0 and R is 1, then reset operation will happen. That is, the present state of the flip-flop is changed to the reset state, that is changed to state 1. Okay, so the reset operation is happening there. If you are giving S as 1 and 0 as R as 0, then you are doing the set operation, that is irrespective of the present state, the result, the state of the flip-flop will be changed to 1. Okay, so you have to understand, if you are giving 0 1 as input, 0 1 as input, you are doing the reset operation, the present state is changed to 0. Okay, if you are giving 1 0 as input, the present state will be changed to 1. Okay, that is, set means setting to 1, reset means resetting to 0. Okay, then if you are giving S and R as 1, it will lead to a metastable state. Okay, uh, the circuit symbol is given, as well as the circuit is given for SR latch. um, Cross feedbacking is happening there in SR flip flop, sorry, SR latch. Okay, then we are moving on to the SR flip flop. moving on to Moving on to the SR flip flops. You can see flip flops are clocked latches with a clock symbol. You can say it is as flip flops. There are four flip flops you are going to study. First one is SR flip flop. This like SR latch, um, but you have to detailedly understand what is SR flip flop is. So the truth table is much more detailed. Okay, S and R and Qn. The value of Qn is the present state, and Qn plus 1 is the next state. Okay, then if you are providing the value input S and R as inputs, the present state of the flip-flop, that is Qn, is changed to next state of the flip-flop, which is denoted as Qn plus 1. Okay, so detailedly we are going to check the states of the flip-flop when you are giving the inputs. Okay, as I already said, S is set. S is for set operation, the flip-flop is set to 1. R is for reset operation, the flip-flop is reset to 0. Okay, let's see. S, R and Qn, the three combination of input, and Qn plus 1 will be the output. Okay, and based on the change of the present state to next state, that is Qn to Qn plus 1, we are doing a statement. We are writing a statement. Okay, well, if you are providing 0 0 as input, the present state can be 0 or 1. Okay, for first case, the present state is 0. Then As we said, there is no set and reset operation, so the present state as it is continued, no change will happen. So for q0, for qn 0 or 1, whatever will be the present state, that will be continued to the next state. So qn is 0, then qn plus 1 also 0. If qn is 1, then qn plus 1 is also 1. Okay, then you are providing 0 1 as input, 0 1 as input, and qn can be 0 or 1. Okay, if you are providing 0 1 as input and 0 is the present state, then what will happen? Yeah, here the value of reset is 1. You have to do the reset operation. Here already the present state is 0, then there is no change has to be happen, so 0 will be continued. If you are providing 0 1 as input and 1 is the present state, then you can do the reset operation here. That is 1 of the present state is changed to 0 as the next state. So the reset operation is happening here. Whatever may be the present state, the value of the state will be changed to 0 if you are applying a reset operation, that is making r as 1. If you are make then next combination s equal to 1 and r equal to 0, so you have to do the set operation. Set operation, whatever may be the present state 0 or 1, you are getting the next state as 1. 0 is moved to 1. 1, if the present state is 1 itself, then it is continued. So the set operation is happening there. Then moving on to the next combination, that is set and reset is 1. If both the set value and reset value is 1, uh, irrespective of the present state, the circuit or the flip-flop will be confused what to do. Either do the set operation or do the reset operation. So it maps to an invalid state. Okay, that invalid state has to be mapped non-care symbol, which is noted as cross in qn plus 1, which is called as don't care. Okay, if you're mapping the result to the truth table, you can see there are three input and qn. The k-map representation will be as given. Here there is a consideration that you can map to the k-map to group with 1. Okay, here you will be getting the plotting like this, and you can draw two groups here, one with 4 members and the another one with 2 members. The equation is being solved based on that. You are getting the two terms s plus r bar qn. Here the value of r is 0, that is why r bar, then qn is as it is, its value is 1, and then s value is 1, so s is simply as it is. So the characteristic equation, that is qn plus 1 equal to s plus r bar qn for SR flip-flop, and the circuit representation is also given. Okay, moving on to next flip-flop, that is JK flip-flop. uh, just like let's look at the truth table. Truth table is similar to that of SR flip-flop. The exception is the last case, that is providing the S and R value as 1. So here JK flip-flop is used to avoid the issue like the metastable state. So you have to give a solution for that state, metastable state. All the other input combination gives the same result as it is, uh, only for the last combination of input, that is 1 1, the change you can see. Here also J resembles to S and K resembles to R value. Okay, if you are giving J as 1 and K as 1, then the present state, based on the present state, the next state will be inverted. Okay, if you are having the present state as 0, then the next state will be 1. If you are having the present state as 1, the next state will be 0. That is toggling. Inversion is happening, toggling is happening here. So if you are giving the input J and K as 1, then the present state will be inverted to get the next state. This is the only change with the truth table of SR flip-flop. Okay. So then you can map the four values of Qn plus 1 into the K map. You are getting the plotting like this, and getting two groups, uh, each of this with two members. Okay, you are getting the equation of Qn plus 1 as J Qn bar plus K bar Qn. Okay, so this is has to be plotted to the circuit, which is given in detail. You can see here in this JK flip-flop, you have to connect JQ bar and K bar Q. Okay, uh, here what is the purpose of JK flip-flop? It is just used to overcome the drawback of SR flip-flop. So the last condition is being changed with that of SR flip-flop. So you can build the JK flip-flop based on SR flip-flop itself. So you are providing the input S and R value as the characteristic equation of JK flip-flop just we obtained before. So you are providing the J as input and cross feedback the result of Q bar with J is an AND gate, and the result is connected. J and Q bar result is connected to S. If you are providing the K as K bar input itself, there is no need of using a NOT gate. If you are providing the K value, then you have to make it a negation operation on that and have to use the NOT gate. Here we are providing the K value as it in the negation form. So there is no need of using NOT gate here. You are providing the K value and cross feedbacking the result of Q with the AND gate, getting the result of K bar Q, which is given to the R gate, R portion of the SR flip-flop. Then the whole combination which is noted with a symbol box, um, altogether known as JK flip-flop. Here into the JK flip-flop you are providing the input as J and K only and getting the result Q and Q bar on the output side. All the remaining inner parts are combined to form the JK flip-flop. This is all about JK flip-flop. You can draw the JK flip-flop based on SR. Okay. Then the next flip-flop, that is D flip-flop, which is called as delay flip-flop. You are giving an input to the flip-flop. After a time delay, the same value will be displayed on the output side. Okay. Here also D flip-flop is implemented with the circuit diagram with the base of SR flip-flop. Before that you can see the truth table, that is D is the input, Q is the output. Here simply you can say 0 is the input, then you are getting the result as 0, and if you are giving 1 as input, you are getting the result as 1. So the characteristic function Q as 1 will be equal to D, the input itself. Okay, you can implement the circuit diagram that is represented here. You can see we are having only D as input. Okay, D as input. So you are providing the result to the value to S and R as well. For that purpose, you have to connect the D directly to S and the negation of D to the R. We are getting the result of Q and Q bar. So if you are providing 0, you will be getting 0 after a time delay. If you are providing 1 on the input, you are getting the result 1 on the with a time delay. Okay, here a symbol box consists D flip-flop. Altogether you are providing the input D and getting Q and Q bar as result. Okay, this is all about D flip-flop, which is used to store elements in counters. Okay, then moving on to next flip-flop, that is T flip-flop. T is for toggling. As we studied in JK flip-flop, toggling is the process of inversion. Okay, if you are enabling the value of T, that is T equal to 1, then the present state will be toggle to next state. Okay, for that purpose we can write a truth table like this. You can see t value is 0, and qn can be 0 or 1. If the value of t is 0, then the state will be continuous as it is. Present state will be continued. If the value is 1 for t, that is toggling is enabled, then present state is 0, the next state will be 1. If the present state is 1, the next state will be toggled to 0. Okay, this can be represented like t. If the value of t is 0, then qn plus 1 will be qn. If the value of 1 for t, and the qn plus 1 will be qn bar. Okay, you can plot it in the k map, and you are getting two separate groups, that is two terms that can be noted as qn plus 1 equal to t bar q plus t q bar. Okay, uh, considering the circuit representation, you know that jk will be the flip-flop which is doing the toggling operation. This is why jk is the base for t flip-flop. Okay, and the value of input is single here, so you have to provide the value of j and k. You are not using a negation operation because j and k should be 1 for the purpose of toggling that we are studying in the jk flip-flop section. Okay, j and k value should be 1. So if you are giving t as 1, then j and k will be 1. If you are providing the j and k value as 1, the jk flip-flop will do the toggling operation. This is why we are using jk flip-flop as a base for the t flip-flop. Okay, you can expect an question like that. Can you able to implement a t flip-flop using SR flip-flop? You can draw the detailed JK flip-flop in the position of this JK symbol flip-flop representation. Okay, so that you can implement the JT flip-flop using SR. JK flip-flop is based on SR, so you have JK flip-flop based on SR in case of T to represent T flip-flop with the base of SR flip-flop. Here we have plotted T flip-flop with the base of JK flip-flop. If you are asked to represent the T flip-flop with the base of SR, then you have to draw the full diagram representation of JK flip-flop which combines, which has the base of SR flip-flop. Okay, so this is all about T flip-flop. This question was asked last year for your university exam. Okay, then application of flip-flop. Flip-flops are used for parallel data storage and serial data storage, transfer of data and counting purpose, then conversion like parallel to serial and serial to data conversions. Okay, then moving on to the difference between latches and flip-flops. You can see latches are built from logic gates and flip-flops are built from latches, and latches will works on input at enable bit, and flip-flops will works on input and clocks. Clocks are important for flip-flops, and latches will send or receive the data when the switch on, but flip-flops send or receive the data based on the signal change. Considering the latches, level triggering is used. For the flip-flops, edge triggering is used. This is all about latches and flip-flops. Here we were covered all the basic flip-flops and the concept of latch and triggering, and we given an introduction to the second unit. Okay, this is all about today's section. Okay, thank you.